Okay, Algebra 2 fans, our topic for today is polynomial functions and curve fitting. So before we start, let me give you your joke of the day. What do you call a pig that knows karate? And the answer is a pork chop. Okay, so we've got a couple things we're going to do here. Our objectives today are to identify polynomials and their degree, to identify the zeros of a polynomial and their multiplicity, and then to analyze the graph of a polynomial function. So the first thing we're going to start with is the definition of a polynomial function. So what does it mean to be a polynomial function? Now, symbolically, f of x, so function with respect to x, equals a sub n, x raised to the nth power, plus a sub n minus 1 times x raised to the n minus first power, plus. Okay, it keeps going, so on and so on, until eventually you get to a sub 1 times x plus the last value a sub 0, which is the constant. All right, now it gets confusing with all these a's and n's and all of that. So the thing to remember is that the a's are the coefficients. Those are just numbers. A sub n is just the nth term. In this case, we will define a sub n, that's called the lead coefficient. The lead coefficient. That's going to be really important. Now, you're going to have all kinds of numbers and exponents and stuff, but a sub n is going to tell you quite a bit. A sub n and then times x to the n is what we call the lead term. That's the first term. A sub 0, the last term, notice there's no x there. That's because that's the constant. A sub 0 is what we call the constant. So all of those a's are just numbers. Okay, a sub n minus 1, they're elements of the real numbers, and we're also assuming that n is a non-negative integer. So n, notice those are going to be your exponents. So let's say n is 3. It would be x to the third, and then x to the 3 minus 1, that's x squared, and so on. X to the first. The constant, technically, it's x to the 0 because that's 1. Now we call n the degree of the function. N is called the degree. So as an example, f of x equals 4x to the third plus 3x squared minus 5x plus 15. The degree of the function is 3. That's the highest exponent. So that right there, that x to the third, that exponent is your n. Okay, so that's the degree. Now we've already talked about polynomial functions because we've talked about quadratics, x squared plus 2x minus 1. The degree is 2. That's a polynomial function. We've talked about linear equations. 3x plus 7. Well, the degree there is 1. So when you're graphing lines, that's a first degree function. When you're graphing a quadratic, that's a second degree function. So polynomial, poly means many. So it could be, the degree could be 1 or 2 or 3, or it could be higher than that. Okay, so the parts of a polynomial graph. Now there's a lot of stuff we're going to write down for this. First of all, the description of a polynomial function. The curve here is an example of a polynomial function. So you'll see there's all kinds of turns here, and the end behavior on the left, this is going down. On the right, this is going up. Now that could switch, it could be different. But the idea of a polynomial function is we describe it as smooth and continuous. What smooth means is that you have no corners. No corners. Now a corner would be something like this, where it just hits and it goes back. It's kind of like an absolute value function. Absolute value is not a polynomial because it has a corner right there. And also something called no cusps. A cusp would be where it kind of comes up or down, and then it does one of these. Okay? So that would not be, those would not be polynomial functions. And the idea of continuous is that there are no holes. No holes. A hole would be something that we saw with a piecewise function where your function might stop and then you have an open circle, then continues. That's a hole. Also, no gaps. So a gap would be something like, all right, it stops there, but then it starts up again right there. That would be a gap. Okay, so with a polynomial function, you can't have any of this stuff. The domain is always going to be negative infinity to positive infinity. Okay, all real numbers. All real numbers. So for polynomial functions, domain is negative infinity to positive infinity. Now the end behavior, it depends on the direction up or down that the function's pointing. In this case, as x approaches negative infinity, so as your x's go to the left, notice that the function itself is going down. So f of x approaches negative infinity. It's going down. End behavior, those are the y values. End behavior is the y values, domain is the x values. Now as we move way off to the right, as x approaches positive infinity, notice that the function now is going up. So we're going to say f of x approaches positive infinity. It's moving up. Now, not every polynomial function is going to end those ways. They might both be going up. They could both be going down. And one could go, it could go up this way and down this way. So for this example, as x approaches negative infinity, the function's approaching negative infinity. As x approaches positive infinity, the function, the y values are approaching positive infinity. Okay, now the parts. So let's go ahead and label what we see here in the graph. The most important points, the points that we tend to focus on, are where we cross or touch the x-axis. In this case, we have 4 of those. Here, 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 and here. Now we have some different names for this positioning. We call these zeros. And I'm going to draw some arrows here. Okay, and then we also have the zeros on the right side. Other names, though, we call them zeros. We also call them x-intercepts. We call them roots. And if we're solving it as an equation, we call them solutions. Those are the values for x that make the function equal to 0. Okay? Now, in terms of the zeros, one of them is different from the others. Notice that the second 0 here, it does not go through the x-axis, it just hits and it bounces back. That's a special kind of 0. And there are a couple ways we describe it. We call this a root of multiplicity 2. Root of multiplicity 2. What happens is that this is actually, it's a root twice. Think of a parabola. When you have, for example, y equals x squared. So when we have, y equals x squared, and we graph that. Notice that what it does is it hits off the x-axis, but it bounces back. So what happens is you have the same answer twice. If we have y equals x squared plus 6x plus 9, so there's your graph. If you were to factor that, it would be x plus 3 times x plus 3. So you end up with the same factors twice, so it ends up being the same solution twice when you solve it. Okay, so if you have this situation where it bounces back like that, we call it a root of multiplicity 2. A name that is probably a little bit easier to say is we call it a double root or a double zero. Double zero or double root. So what happens is you get the answer twice. It's the same thing. And the idea is that it bounces off the x-axis. Bounces off x-axis. Okay, now all the other zeros, notice they actually go through, except for this one. So this goes through, this goes through. So this would be the root of multiplicity 2. All right, so those are zeros. Now some other points that are going to be important. Y-intercept is when you cross the y-axis. And then you also have the points where we're turning. And what we call those are turning points. So this right here is what we call a turning point. For this part of the function, notice it's the highest point. Now, we call that a maximum, but in this case, it is called a local maximum. It's not the highest point on the whole function, because notice to the right, this is going up to positive infinity. But in the locality, in this area, that would be the maximum. Down here is another turning point, but this would be a local minimum. So a local min for that. Now also, here, this would be a local minimum. It's also the 0. And this would be a local maximum. It's also the y-intercept. So notice we have 1 turning point, 2, 3. So we have 4 turning points in this function. So there's a lot of vocabulary when you're talking about polynomials. Okay, now a couple examples here. Are these polynomial functions? If so, then what is their degree? So a polynomial function, the exponents have to be non-negative integers. Okay, so this is y equals x to the third minus 2. That's a yes. That's a polynomial function. The degree is 3 because the highest exponent is 3. Now number 2, 3 times the square root of x plus 4x squared. The problem here, the square root of x, we could write that as a rational exponent. Okay, you remember doing this? This would be, since it's a square root, this is x to the first, we could write the exponent as 1/2, 3x to the 1/2. Now in the definition, n is a non-negative integer. So it can't be negative, it can't be, and it also has to be an integer. So it can't be a fraction. So 3x, that's a fraction exponent, so that is no, that's not a polynomial function. H of x equals 15. Now there's no x, but technically you could write it as x to the 0, which is 1. So that is a polynomial function. If you graph it, it's a horizontal line. We would say the degree is 0. Number 4, x squared plus 3x divided by x to the third. Well, what we could do from that is we could break that into x squared over x to the third plus 3x over x to the third. And if we subtract the exponents, we're going to get 2 minus 3 is negative 1. We get x to the negative 1. And then this would be 1 minus 3 is negative 2. That's 3x to the negative 2. Now normally we wouldn't leave it like that. X to the negative 1, we would write that as 1 over x. And this would be 3 over x squared. But notice that your exponents are negative. That does not fit the definition of a polynomial function, so that's a no. And then the very last one here, x minus 3 times, parentheses, x plus 2 squared. If we were to multiply this out, then what would happen is that you would get, that's x to the first, and then here this would be x to the second. If I square this out, I'll get x squared, okay, ignore the sirens there, plus 4x plus 4 if I double distribute. And then if I multiply one more time, if I distribute again, this would end up being x to the third. Everything, we're going to have a bunch of terms here, but all the terms will fit the definition of a polynomial function. It's going to be yes. The highest degree would be when I do x to the first times x to the second. It'll give me an x to the third for my lead term, and so the degree would be 3. And that's the end of part 1.